In this video, we're going to discuss special types of ring homomorphisms. In particular, we're going to define what a ring isomorphism is. Now, what we're going to do is we're going to first of all note that if phi is a ring homomorphism, then it is a function. And as a function, we can ask the questions, is phi one-to-one? We can ask, is phi onto? And we can ask, is phi both one-to-one and onto? And whether or not a particular ring homomorphism has one or both of these two properties actually turns out to be fairly important, and I do want to introduce just a little bit of vocabulary. Many people will say that if phi is one-to-one, they will refer to phi as an injection. So an injection. And some people will even say that phi maps R into S as an injection. When phi is onto, we typically, some people will refer to this as a epimorphism. I don't like that language, but you should be aware of it. So if phi is onto, then some people will call phi an epimorphism. But the main thing that I want to think about is that phi is onto is often referred to in English as phi maps the domain ring onto the target ring. So if you see this kind of language describing phi, it means that we know that phi is onto. And when phi is both one-to-one and onto, we're going to give that kind of a function a special name. So if phi is both one-to-one and onto, we call phi a ring isomorphism. And it's important to realize that the iso part of this is a Greek word meaning same. It's a Greek root, and it means same or equivalent. And I want to kind of get into that idea, and I also want to make a little bit of a notation note. So the first thing is some notation. If we have phi being a ring isomorphism from R to S, then the first thing is notationally we write R is isomorphic to S. That's red. R is isomorphic to S. And what this means is that R and S have the same algebraic structure. And we'll actually look a little bit about what that means in a few minutes in a specific example. But basically, I want to point out that the symbol that we are using here for isomorphism is the same symbol that is used in high school geometry classes to denote congruency. And the reason why we are reusing that symbol is that congruency and isomorphism are very closely related concepts. If two triangles are congruent, they basically are the same triangle except for where they are located in the plane. And if two rings are isomorphic, they have the same algebraic structure, and the only difference is what we've chosen to name their elements. So basically we have the same ring but in two different flavors, so to speak. So when two rings are isomorphic, If R is isomorphic to S, what this basically means is that we have the same kind of structure with different names. So we have different names for the elements. Now, there's one other thing that I want to point out before looking at a specific example, and that's about the isomorphism itself. Now, if phi takes R into S is an isomorphism, then it turns out that phi, of course, has to be both 1 to 1 and onto, and that's enough to say that the inverse map phi inverse going from S to R is defined as a function. And phi inverse is also going to be a ring homomorphism. And I want to look at that as well. So let's look at this idea for just a few minutes. So the idea is that if we have a ring isomorphism and we have R here and we have S here, the map is going to be 1 to 1 and onto. Now what that means is if I take two elements over here in R, they have to map to separate elements over here in S. So we have phi of R1 is equal to S1. We have phi of R2 is equal to S2. That's what the 1-to-1 part of phi is a ring isomorphism is going to say. But the onto part is also going to give us some stuff. If we have a particular element over here in S, the fact that phi is onto means that there is somebody over here in R that had to be sent to that guy. And moreover, there is only one somebody. And this particular element is often called phi inverse of S. Phi inverse of S is the pre-image of the element S, and I'm just going to call this guy R hat right now. And we know that because phi is onto, that there is an R hat in R with phi of R hat equal to S, and because phi is 1 to 1, we know that R hat is the only element in R with the property that phi of R is equal to S. Now, what this means is that if we think about this, we can essentially turn all of these arrows around the same way we turn that green arrow around to find the pre-image of S. And we can turn all the arrows around and we will get a map phi inverse going from S into R. And the basic definition of this map would be that phi inverse of S is going to be equal to R if and only if phi of R is equal to little s. And so this is a basic important property of ring isomorphisms, that they always come in pairs, one going from R to S, and then one going back from S to R.